Okay. So, in the previous lecture we have discussed about discrete integral controller, right, for AGC. So, this already we have discussed. So, this block diagram I told you that power system is in continuous time domain and controller is always in your discrete domain, right, and this is the sampler and this controller is there, 0 order hold is there. So, I told you that whenever you will solve, I mean nowadays you are putting in the MATLAB and getting the result, but my suggestion is that if you write the code of your own, you have to follow this logic. So, this is your what you call, this is the controller and this is your 0 order hold, right. That means, after every sampling instant, that suppose if it is integral controller, that u will be evaluated and it will be hold till next sampling instant comes, and this power system is a continuous system. So, mathematically when you will do it, that you have to integrate it, you have to follow some numerical methods, right. So, that if the logic is like this, then we will come back to this. All sampling time, other things we have discussed. Now, that continuous integral your what you call that equation, that continuous mode, that control law, that UIT for ith area, that minus KII integral of ACIT dt, this is equation say 50, right. Now, the discrete version of equation 50 is computed directly as ui kt, k is the sampling instant and t is the sampling time. This way we write is equal to ui k minus 1 t minus KII into t into ACI kt, right. So, I mean it is, I mean if you, I mean it this kind of thing, I think you know it, that suppose when you find out, suppose u is equal to, for example, say x dt say, right. Therefore, u dot is equal to, forget about other gain anything, x dot is equal to actually x. So, this can be written as x k plus 1 minus x k divided by delta t. This is actually derivation approximate definition of derivative, that x k plus 1 minus x k upon delta t, right. So, this is, so whenever you do this, and sorry, just 1 minute, sorry, there is one mistake, sorry, that u is equal to your integration of x dt, right. Therefore, u dot is equal to x. So, this side is u dot, sorry, this side I thought it is x dot. So, it is actually u k plus 1 minus u k divided by say delta t is equal to x k, right. That means, my u k plus 1 is equal to u k, right, then plus your delta t into x k, right. So, this is your what you call that your that u we can write. Similarly, when it is uit, you take the derivative of both sides, then it will be minus ki then ACI, right, forget about t. Therefore, uit your ui dot is equal to minus ki ACI, I mean it will be like this, ui dot is equal to minus kii then ACI, right, but sampling time is t. That means, this one can be written as the way we are writing here, say ui kt minus ui your k minus 1 t divided by t, right, is equal to your minus kii ACE kt, right. So, just cross multiply and do this. So, this will be your equation, that is your ui kt is equal to ui ki minus t minus ki, that means every sampling instant, say if t is equal to 2 seconds, you find out what is the value of u till next sampling instance come, that is t is equal to 4 seconds, this signal will be held constant till the next sampling instant come. When t is equal to 4, again you compute till the next sampling instant 6 comes, because t is equal to shift sampling time is t is equal to 2 seconds, right. Where k is the, it is given k is the sampling count and t is the your sampling time, right. So, one more thing is there, that is your in this block diagram, that now this one controller we have kept first, next 0 order hold. So, if we make say rather than 0 order hold first, say for example, suppose instead of controller, say this is 0 order hold and this is my controller. So, how things will look like? So, this is 0 order hold and this is controller. So, in this case what will happen, that this is sampler and suppose AC will be sampled, right. In that case what will happen, that AC will be held constant till the next sampling instant come, and this controller now is in continuous time domain, right. It is a continuous control law will be continuous time domain. So, in that case this integration will be in the what you call in that continuous form, and then this system also continuous. That means, in that case that every integration's time whatever you take, whatever numerical methods you use, right, you have to evaluate this one, but this AC will be evaluated at every sampling instant. For example, t is equal to 2, then t is equal to 4, t is equal to 6, but this integration will be continuous, right. So, both the things if you put for example, in MATLAB and try to see the responses, you will find apart from very closing to the settling time, both responses are more or less same, right. So, this is your what you call that discrete that what is the reality actually. So, next is that some exercise, after that again we will come to this we will do it because I have to save some time, right. So, first example is that a system consists of 3 identical your 500 MVA generating units feeding a total load of 765 megawatt. The inertia constant H of unit is 5 on 500 MVA base, that is 5 second actually, right. The load varies by 1% for 1% change in frequency. When there is a sudden increase in load by 50 megawatt, increase in load means that frequency will decrease, assume F0 is equal to 50 hertz, right. So, you have to determine that H and D expressed on 1500 MVA base, and second one is find the steady state value of frequency deviation and its mathematical expression, assume there is no speed governing action. One examples we have seen, right. So, you will derive this and this you will find out, and this is the actually answer, right. Second thing is, second example is that an isolated power system consists of 3 turbine generating units rated 1000, 750 and 500 MVA respectively. Regulation of each unit is 5% based on its own rating. Initially each unit was operating at half of its own rating. When the system load suddenly increases by 200 megawatt, determine the area frequency response. So, answer is given, beta is given, right, and area frequency response means that beta area frequency response characteristic, and all the answers are given. Now, next problem is that you will do it. Consider a 2 area power system interconnected by a tie line. Area 1 has 1000 megawatt of total generation and R1 is equal to, it is 350 inverse, that is 1 upon 350 hertz per megawatt, and area 2 has 2000 megawatt of total generation, R2 is equal to 700 inverse, that is 1 upon 700 hertz per megawatt, right. Initially each area was generating half of its total generation. Assume D is equal to 0 and U is equal to 0, that is U is equal to 0 means uncontrolled, and D is equal to 0 also you assume, and system frequency F0 is 50 hertz. Compute all these quantities, steady state values of frequency, generations and tie power for a step increase of 100 megawatt load in area 1. So, these are the answer, right, these are the answer. Next one is next one is consider a single area system as shown in figure 26, that is this figure. With PID controller, obtain the dynamic responses and compare it with only integral controller. So, this is actually simulation purpose, no need, just a PID controller is given, right. So, in this case how we will actually that MATLAB, that is your MATLAB simulating block, right. MATLAB simulating block, when you put PID it gives the result, this one I can take Kp dash because this Kp is used here. So, this is different Kp. So, this is Kp dash. So, this is Kp dash plus Ki upon S plus Skd, that proportional integral derivative. So, in general actually this one, if we want to all these values, right, all these values, we say instead of taking this one, the minus Kp, this is minus Ki upon S, this is minus Skd. In this case you will see that Kp, Ki, Kd value all will be positive. If you put plus, it will be minus. Now, question is that how to incorporate for your, when you are writing code, right, how to do this. So, question is that how we will do this. So, here just hold on. So, here your this is your Kp, and suppose you have a PID controller, say this is Kp dash plus Ki upon S plus Skd, say plus is there, it does not matter, right. So, suppose the input signal for this case it is delta f, this input signal is delta f. So, this is actually my delta f, right, and this is Kp. What we will do, that we will take three part, one is U1, another is U2 plus another is U3 and output is U. So, U is equal to U1 plus U2 plus U3, right. So, what we have to do is, and it is multiplied by delta f. So, U1 is straightforward, U1 is equal to Kp dash into delta f, right. This is my U1. Now, U2 actually, U2 is equal to your this Ki into your delta f upon S, right. So, if you cross multiply, it will be SU2 is equal to Ki into your delta f. So, this is actually derivative U2 dot, that is your U2 dot is equal to Ki into delta f. That U2 dot can be written as, so this is U1 is equal to Kp dash f. So, U2 dot can be written as, say U2 K plus 1 minus U2 K, that is K is that your what you call that sampling instant, divided by say delta T is equal to your delta f K, right. That means, my U2 K plus 1 is equal to U2 K, it is actually it was multiplied by Ki, because this Ki term was there. So, Ki delta f, so plus delta T into Ki into delta f, right. So, this is actually my U2 K plus 1, I am rewriting here, that is U2 K plus 1 is equal to U2 K plus delta T into your Ki, the integral gain, into delta f K. This is actually mathematics. So, when you write the code, so initially this K and other thing nothing is there, you have to put in a loop, right, and this your what you call, when you integrate it, so initial values of U2 will be 0, right, and accordingly you have to integrate. So, this is actually your U2. Similarly, for the other part U3 is equal to actually Kd into S delta f, that is nothing but Kd into delta f dot. So, that is nothing but Kd, that is delta f K plus 1 minus delta f K divided by delta T, this is the derivative. So, initially to compute this derivative, in the when you put it in a loop, the initial value of delta f K is known, and this one you are every time you are going for simulation. So, this will be known, every iteration, divided by your integration step length, that will be your this thing, and when you will come to the next iteration, this value should be replaced by this value, right. So, this way actually you do it, and if you look into in the form of your block diagram, then this is my delta f, then you have to make three part, one is Kp dash, the proportional gain, another is Ki upon S, the integral part, right, another is that derivative part Skd, right, and here you have to sum all, all plus plus. So, this one we took A1, this one we took A2, U2, and this one U3, and this is my output U. So, when you write the code, all three you have to compute separately, then you have to add, then you will get the U values, right. This way we do, right. Now, just hold on. So, whatever parameters till now we have used, earlier also I told you these parameters are given. What I suggest for this one, for this kind of thing, just you can put in a Simulink and you can see that what is that your what is some values of, look I told you, no, as we have taken your what you call that your this all plus in positive, all positive, that is why Kp minus, it is Kp dash, this is actually Kp dash, Kp dash minus 0.4, Ki minus 0.7 and Kd minus 0.5. If you take all minus, all should be plus, and step load input is 0.01, right, because this Kp, do not be confused with this Kp, this is Kp, this is Kp dash, this is proportional gain, this is your derivative gain Kd, and Ki is the integral gain, right. Another one is that suppose an area is interconnected with another area having extremely large capacity. I told you when we are discussing about this, after that we will go to the deregulation. Infinite capacity as shown in figure 27, obtain the dynamic responses of this system with and without considering integral controller. So, this in this problem, that as I told you that that if the area 2 capacity is very high, then you will find there is almost no frequency deviation for a load disturbance in this area. So, that means delta F2 is 0, but tie line should be there, it is there. So, in this case I am not asking you to do simulation. What you will do is that you please find out your what you call that your steady state error, that is delta F1 SS is equal to how much, and delta P tie 1 to SS, right, is how much. This is an exercise for you for a step input, delta PL, right, in terms of delta PL. Now, another thing is that regarding your optimization. So, different type of performance indices are available for finding out the gain setting of the integral controller or other or your what you call that PID controller or other type of controllers. So, for integral controller, say in this case you have one delta F and one is delta P tie 1 2. For 2 area also we have delta F1, delta F2, delta P tie 1 2, but for isolated system we have delta F, right. So, whenever we take, say for isolated system, say when it is isolated system, right. So, isolated system actually this thing is not there, this part is not there, that we have seen also, right. Only this thing and this part is also not there. For isolated system actually directly it will go to your what you call minus Ki upon S, because B is not the, your what you call for isolated system, it is simply a direct feedback, right. So, for isolated system your, if we take an performance indices, say integral of your delta F square dt, right, it is an integral square error technique. If you use that J, that objective function for optimization, you have to go for this objective function, say J is equal to delta F square dt, and your objective is that you minimize this function, you minimize the function J for isolated system only, right. So, generally different other type of performance indices are there, but this thing has some meaning. Meaning is that basically it is written integration of delta F square dt. If you if you go on, if that your what you call that delta F deviation, for example, suppose this is my 0, this is origin and this is my, this axis is my time axis. Suppose response is like this, response is like this, like this, like this, like this, right. So, when error is large, this is my delta F frequency deviation. When error is large, its square will be also large, and his error is small, his square will be also smaller. So, this integration one, if we make it like this, say if I make it like this, k is equal to 0 to infinity, say delta F k square, right, dt I can make it here, say this is delta t, right, because it is multiplying again and again. So, then k 0, discretizing, k is equal to 0 to infinity delta F squared k, right. Now, for k is equal to 1 to 3 means it is sampling instant, that is your integration time is increasing, right. So, in this case what will happen, when it get this value, this value, this value, its value is high. So, its square is higher. So, in summation that higher your what you call large error actually will get more importance. But suppose if you put some threshold here, so when it is coming in this range, say, So, here error is small, delta f is small, its square will be much smaller. So, in this addition term its contribution is negligible. That means the significance of this is that this kind of your objective function, it penalizes large error heavily and small error lightly. That means small error it does not take care, but it takes the large error, right. Accordingly, if you minimize this objective function to get the Ki. So, details are beyond the scope for this course because of your because we have to think from the point of view of your classroom exercise. Similarly, for two area system also we can take objective function, that is j is equal to integration of say del f1 square plus delta f2 square plus delta peta i12 square into dt. So, similarly, it can be optimized Ki, Kp, K your proportional gain, integral gain, derivative gain or any other form of controller, but you have to follow some optimization technique, mostly soft computing techniques are more suitable for this, but that is beyond the scope, right. Then whole soft computing technique, then I have to tell to do this, but that is beyond the scope. So, with this that deregulated this conventional AGC part I had to cover, because otherwise we will fail to understand that your what we call that your deregulation one, right. So, now we will go to the AGC in restructured environment or your deregulated environment, right. So, we will go to now that AGC in deregulated environment. So, we call that automatic generation control in restructured power system, that is deregulated environment. So, first let us see this little bit of introduction. So, in a restructured power system, the engineering aspect of planning and operation have to be reformulated, although the essential ideas remain the same. Look, power generation, transmission, distribution, that power has to be generated and it will go through the transmission to the distribution side. So, your what you call essential ideas remain same. Some countries, I mean some countries, right, they are along the path of restructuring than others, and it is becoming clear that there will be many variation in the restructured scenarios for electric power systems around the world, right. The electric power business at present is largely in the hands of vertically integrated utilities. The meaning of like this, that vertically your integrated utilities, the meaning is that means suppose you have a power system and you are the owner of generation, transmission and distribution all together, right. So, that is called actually vertically integrated utilities. Suppose one utility is owning its generation, transmission and distribution, right, and that supply power to the customer at regulated rates. So, that is we call the conventional thing or vertically your what you call integrated utilities. Now, such a configuration is shown is conceptual in figure 1. I will come to the figure 1, in which the large rectangular box denote VIU. The VIU is usually interconnected to the other VIUs. I will come to that figure, and this interconnection is almost always at the transmission voltage denoted in the figure as tie lines, right. Thus, electric power can be bought and sold between vertical integrated utilities among the your what you call among these tie lines, and moreover such interconnection provide greater your reliability. So, now this is actually my VIUs, the vertical your integrated utilities. That means utility is owning everything, that is your generation, transmission, distribution. These are the generators, right. And then this is a transmission system, and then this is a distribution system. Apart from that, private parties are there, that is IPP, that is independent power producer. So, this independent power producers, their system may be directly connected to the transmission system, that is a high voltage level. Some independent party other independent power producers, their system also may be connected at the low voltage, that is at the distribution level, right. This is also some independent power producers, part of the generators directly connected to the high voltage side transmission system, and some of it generators generating power at low voltage level. So, directly connected to the distribution system. So, basically if you own that everything generation, transmission and distribution, so accordingly that power is what you call you are selling to the distribution side, including your all sort of consumers. And tie lines are there, these tie lines, that means this power system is interconnected with some other power systems, other VIUs, right, vertically integrated utilities, and selling and buying actually the purpose is served through the your what you call through these tie lines. So, this is actually the conventional power system. That means that you are the owner of generation, transmission and distribution together, right. This is the concept of your what you call that your vertically integrated utilities, right. Now, the concept is changing. Concept is changing means that suppose given the present situation, it is generally agreed that the first step in deregulation will be separate the generation of power from the transmission and distribution. That means generation you separate from the transmission and distribution, then putting all the generation on the same footing of the IPPs. IPPs means that is your that is private parties, I told you, independent power producers. That means generation, all the, I mean what you call, you separate generation, you separate transmission and separate distribution. So, like independent power producers, they are also separate, right. So, if you do so, then you will have a separate 3 different entities, one for generation, one for transmission and another for distribution. So, even IPPs also will come into that generation, that is separate, right. So, figure I will come later. So, figure 2 shows that deregulated utility structure. In figure 2, generation company we call GENCOs, right, which will compete in a fee market to sell electricity they produce. Actually, what happened in this case, the generation company, transmission company and distribution company, 3 companies are there, right. That power wheeling will be through the transmission system, right. Now, question is that there must be some separate entity, I mean impartial separate entity, that is called your independent, your ISO, that independent system operators, right. Their bidding will be there. The generation companies will give bidding that this hour, this is the price of the electricity, that is the energy, right. And power has to flow, power wheeling through the transmission system, and you have distribution system. So, that is we call, generally generation companies we call GENCOs, transmission companies we call TRANSCOs and distribution companies in short we call DISCOs, right. So, that is distribution companies, hence I will tell DISCOs, right. It has every right to buy power from different GENCOs, right. Suppose there are several areas are interconnected. Suppose I am sitting here at Kharagpur, I have some power, I have some generating power plant here, I have some distribution companies here, right. But another power plant, say somewhere in Bhubaneswar, there also you have several generation companies as well as distribution companies. But if I find the power is cheaper, if I buy it from the generation companies from the your Bhubaneswar power plant, then I may not buy the power from the generation companies of the Kharagpur. So, this is the flexibility in deregulated power system, right. So, that is why that your and that is why we are separating three things, the generation companies, transmission companies and the distribution companies, right. So, that means your that GENCOs which will compete in a free market to sell electricity they produce, it can be assumed that the retail customers will continue for some time to buy from the local distribution company, right. Such distribution companies have been designated as DISCOs, in short we call distribution companies, which in short we call DISCOs, right. The entities that will wheel this power between GENCOs and DISCOs have been designated as TRANSCOs. So, transmission company we call TRANSCOs, right. Although it is conceptually clear to have separate your functionalities for the GENCOs, TRANSCOs and DISCOs, in reality there will exist a company with combined what you call this or partial responsibilities, that is called ISO, independent system operator. Thank you very much, we will be back again.